Quantum computers, the misunderstood revolution that will guide the 21st century. To understand your future appliance, you first have to understand the one you are looking at. In a computer, everything works in an on or off state, using logic gates to determine operations. In electronics, this looks like millions of transistors representing an on or off state with current flow. On is represented as a 1 and off a 0. Together, these millions of transistors go between logic gates like OR, AND, and XOR to produce an output, like this video on your screen. Quantum computers work similarly to conventional computers, however possess an added exponential complexity. Rather than the conventional bit, which represents a 0 or 1 as electrons in a transistor, a qubit represents a variety of states that only when observed correspond to a 0 or 1. A qubit can be made from trapped ions, photons, artificial or real atoms or quasiparticles. The qubit must be isolated and cannot be observed by anything other than the computer. Think of the qubit like a bird seen through a window. Whilst you aren't looking, the bird could be anywhere beyond the window in any position. When you look through the window, you can see if the bird is looking towards you, a 1, or away, a 0. But you cannot observe constantly. You are required to blink, turn away, get food, and live your daily life. After profiling the bird for many years, you have a probability representing the chance of the bird facing you or not. For example, there's an 87% chance the bird is facing the window. This represents the second piece of information, a probability of position. Together the state, facing or not, 1 or 0, and the probability of being in that state, 1.0, 0.5, 0.87, etc., represent the two pieces of information a qubit can give when observed. This means that at any one instance of time, a qubit can provide two pieces of information, rather than the singular piece of information a classical bit provides. In a quantum level, the qubit state is often represented by its spin direction around a magnetic field, where magnetic poles determine the 1 or 0 state. So when two qubits, or birds, are observed together, a new set of information is present. You could either have 0, 0, 0, 1, 1, 0, or 1, 1 in a conventional computer. But in a quantum computer, to represent the state as a whole, 4 coefficients representing the probabilities of each individual state of the two qubits must be taken into consideration. So at any one time, we now have 4 bits worth of information, the relevant probabilities of each of the classical bit states. In an exponential sense, scaling up to 3 qubits would require 8 numbers representing the state of the system, despite the 3 classical bits worth of data. Generalizing, we find that the amount of information n qubits represent is 2 to the n classical bits. So with 300 qubits, we can represent 2 to the 300, or 2.03703598 times 10 to the 90 pieces of information, which is more than the amount of atoms in the universe. We cannot measure the probabilities during our calculations of qubits, and when observing the bit, it must fall into the position represented by a classical state. So despite having 8 pieces of information on the position of birds out of the window, only 3 bits will ever be interpreted, the actual facing directions. But the qubit cannot just be read or written to in the conventional manner. A qubit must be completely isolated to function correctly, as it is extremely fragile and it will decohere, destroy its state, to any amount of noise or interference, including reading the value from the qubit. So a qubit has to be trapped in a material of extremely low temperature, only a few hundredths of a degree above 0 Kelvin, to ensure it doesn't automatically decohere, and it must be surrounded by a material of no magnetic resonance, or no nuclear spin. A good example is silicon-28, which is being used by researchers around the world with electrons on electronegative ions to produce a qubit. The electrons on the ion spin around the ion within the magnetic fields, and when they have maximum energy, they can spin around in the opposite direction. To read a qubit state differs with the approach taken, but in the case of electron qubits, the qubit must be embedded in proximity to a transistor. As the transistor is pulsed, if the qubit is in an upspin or high energy state of greater than 0.5, it will have enough energy to jump from its atom to the stream of flowing electrons, creating a spike in current. In all other circumstances, it will produce no effect. To write to a qubit requires an electromagnetic wave in tune with the resonance hertz of the qubit, pulsed for long enough to absorb enough energy to flip directions on the magnetic field. The wrong frequency in hertz, and the qubit will not be able to absorb the information. During calculations and usage, the states of qubits change rapidly and can find themselves quantum entangled with a nearby qubit. Their states are now equivalently linked, allowing for a higher degree of computational power, but entanglement is very hard to intentionally achieve and was often ignored in the initial development of quantum computers. Due to qubits' high fragility, a perfectly isolated system is near impossible, so error correction must be implemented. In a qubit system, there is no way to clone a qubit, as when reading one we destroy the data contained. However, they can be shadow cloned to produce near identical qubits. Up to 5 extra qubits have been used to error correct a single qubit before. Qubits in conventional algorithms are slower than conventional computers due to the extra requirements for reading and writing. They provide no benefit whatsoever, but in algorithms which require parallel computation, like simulations and modeling, qubits outperform computers exponentially to the point where calculations that would take thousands of years on a conventional computer take only a few minutes on a quantum computer. This allows for some very useful but specific applications. In very topical terms, artificial intelligence could outperform significantly, as its node-based neural networks can be simulated simultaneously with the aid of quantum computing. Natural language processing within computers can be accurately rather than approximately achieved. The research and creation of better batteries through chemical simulation and modeling is expected to reform the power industry. Drugs and pharmaceuticals, as well as chemicals, can be completely created and simulated from scratch with quantum computer-aided development. Biological and chemical interactions can be modeled, and the electron orbits of atoms can be calculated with higher precision than ever before. Complex simultaneous manufacturing developments can be researched through quantum computing tools, with the expected discovery of new electronic materials. Cybersecurity will be turned on its head, as all conventional encryption could be cracked instantaneously, and new encryption is created. Applications also extend to financial modeling, traffic, and task optimizations. Quantum computing is built off the backbone of quantum mechanics and physics, the idea that at a quantum level, particles can act as waves and waves as particles, that atoms exhibit different properties at the molecular level. The point when quantum physics was first used in computing is a very grey line, but one that I have separated out into many phases to help elucidate the driving reasons for developing the quantum computer. The overarching reason why development has continued is to perform concurrent calculations at once, faster than conventional computers could solve them one by one. So before I get into the history of development, let me elaborate on that statement. More specifically, the concurrent calculations. A conventional computer has a central processing unit, and within this, there are cores. Cores can interact with the hardware simultaneously and with each other, but a single core can only do one thing at a time, so instructions pile up on a single core. Like typing, each key is processed one by one, and whilst this is intended for a home or personal computer for a variety of applications, it provides a few very large drawbacks, the most significant being high-intensity calculations cannot be done at once. So the GPU was invented, the graphics processing unit, and don't let its name confuse you. This machine can only perform concurrent calculations. It takes a matrix of data and applies computer-based instructions to each through matrix-based operations. This allows for suitability for rendering each pixel in a video game, as it has to do well over 6,220,800 calculations per frame or screen refresh. But it requires a CPU to instruct it and has no hardware access. Quantum computing is a CPU and GPU combined, and so much more, yet has its own drawbacks. In terms of processing power, quantum computing uses a combination of single computations, multiple computations, and two new techniques, reverse computations and entangled computations, leading to impossible calculations to become feasible. However, a significant drawback is the single use cases, as quantum computers cannot access hardware and only perform calculations in a non-concurrent way, meaning we have little to no control. The communally agreed origin of quantum computers was Stephen Weisner's 1968 invention, conjugate coding. It was an application describing the method of transmitting multiple messages with qubits so that viewing one destroys the other, acting as a sort of random number generator. His goal was small and with good intentions, to develop fraud-proof banknotes. Then came along James Park in 1970 with his theorem called the no-cloning theorem. The theorem states that it is impossible to create an independent and identical copy of an arbitrary unknown quantum state. This effectively means you cannot store backups of data in case anything goes wrong. So error correction is impossible through classical methods, and data cannot be classically stored quantumly. His goal was to prove that cloning qubits of differing probabilities is impossible. He provided an alternative called shadow cloning, which copies most of a qubit state, but not all. In 1973, Alexander Holevo publishes Holevow's theorem, which states that n qubits can carry more than n classical bits of information, but at most n classical bits are accessible, due to the probability coefficients we discussed earlier. His goal was to show the limitations of quantum states. In 1973, Charles H. Bennett creates reversible computing, which makes some calculations in state physically or logically reversed, essentially being able to reverse and or logic gates to their original inputs. This means that if an operation is logically reversible, the output can be computed from the input and vice versa. Reversible logic gates and circuitry generally have the same number of inputs as outputs, assuming all inputs are consumed and that all output states are possible. Charles' reason for doing this was to improve computational energy efficiency in computers beyond current standards for irreversible operations. And lastly, in the pre-computing age, we have 1976 Roman Ingarden's quantum information theory. It attempted to show that Shannon information theory, another popular theory, could not be generalized for a quantum scenario, but that it would be possible to create a theory which generalized Shannon's theory. It meant that the generalized quantum mechanics of open systems, called semi-observables, would describe computing in a quantum scene. In the dawn of 1980 and the beginning of the modeling and algorithms age, Paul Benioff creates the first quantum mechanical model of a computer. He showed that a quantum computer would function under a Schrödinger equation, describing the operation of a Turing machine. Later in 1980, Tommaso Toffoli creates the Toffoli gate, which is described as a functionally complete logic gate for reversible classical computation. Its official name is the controlled NOT gate. It takes 3 inputs and gives 3 outputs. If the first 2 bits are set to 1, the third bit is flipped. Otherwise, they stay the same. This was the first working proof of Charles B's reversible computing and its energy efficiency. In 1984, Charles Bennett and Giles Broussard, in conjunction with Stephen Weisner, publishes a paper describing the first use of quantum cryptography, permitting secure distribution of random key information between parties who share no secret information initially, provided the parties have access, beside the quantum channel, to an ordinary channel susceptible to passive but not active eavesdropping. We also present a protocol for coin tossing by exchange of quantum messages. Except where otherwise noted, the protocols are probably secure against an opponent with superior technology and unlimited computing power, barring fundamental violations of accepted physical laws. In 1985, David Deutsch creates the first universal quantum computer, which is able to simulate any other quantum computer, with at most a polynomial slowdown. The universal quantum computer makes a quantum mirror of a quantum circuit or quantum Turing machine. It forms the basis as the start of quantum computers and physical models. In 1988, Yoshihisa Yamamoto and Kei Igata make the largest development of the 80s, creating the first physical quantum computer, using atoms to perform 2-qubit calculations and photons to transmit qubits. It is commonly known as the progenitor of modern quantum computing. Ending the age of modeling and algorithms, in 1992, David Deutsch and Richard Joseph develop a computational problem designed to be possible on quantum computers and impossible on classical computers. Along with the paper, they provide an algorithm to which the quantum computer could solve the extreme computational complexity of their problem. In 1994, the experimental age begins, and a familiar name releases his algorithm, Peter Shor and his prime factor reduction algorithm, designed off the back of 1993 Dan Simon's problem. Dan Simon's problem, without going into elaborate and overcomplicated details, showed that certain computational problems involving large numbers and finding components could be solved exponentially faster on a quantum computer than on a classical computer. Shor's algorithm makes it possible for a quantum computer to factorize extremely large integers extremely quickly, solving major limitations in quantum computing design. But it also brings about a method to break all cryptographic encryption in use today. Shor's algorithm is made up of 2 main parts: a classical computed reduction of the factoring problem to the problem of order finding, and then the quantum computer to solve the remainder. Shor's algorithm sparked extreme interest in the quantum computing sectors. Towards the end of 1994, Ignacio Zirac and Peter Zoller proposed the first physical controlled NOT gate out of cold-trapped ions. The idea is to trap and suspend ions in space with electromagnetic fields. The qubits are then stored in the electron states of the ion, allowing transference of data through collective quantized motion of the ions in a shared trap. In 1995, Christopher Monroe and David Wineland create the controlled NOT gate following the previous proposal. In 1998, Jonathan A. Jones and Michelle Mosca host the first experimental demonstration of a 2-qubit nuclear magnetic resonance quantum computer solving Dutch's problem. In 2000, the no cloning and no deleting theorems are proven by Aaron K. Patty and Samuel L. Bronstein, showing that a copy of a qubit cannot be deleted, implying quantum information cannot be created or destroyed. The beginning of the pre-modernization age, and big things are happening. The first execution of Shor's algorithm at IBM's Almaden Research Center and Stanford University was demonstrated in 2001. The number 15 was factored using 1,018 identical molecules, each containing 7 active nuclear spins. 2003 to 2006, University of Innsbruck start making large contributions to the quantum computing sector using the CNOT gate in an 8-qubit register computer. 2006, and the first 12-qubit quantum computer is created by the Institute for Quantum Computing and Perimeter Institute for Theoretical Physics in Waterloo. 2007 marks the age of modernization, where the developments are getting so large and frequent, I had to cherry pick only the very best. 2008, entangled memory is developed. 2008, first qubit written to. 2009, qubit lifetime extended by a factor of 1,000. 2009, quantum entanglement possible over 240 micrometers. 2009, NIST read and write individual qubits, demonstrating many operations. 2009, a universal ion trap quantum computer with no decoherence was realized. 2009, the first microchip-sized quantum computer is reported. 2012, a working transistor is made from a single atom. 2014, data is teleported 3 meters using quantum computers and no errors. 2017, IBM created a working 50-qubit computer that maintains quantum state for 90 microseconds. 2017, data is teleported 1,400 kilometers into space. 2018, Google created a 72-qubit chip. 2020, quantum noise in a chip is reduced to 0. 2021, the calculation is done in 1 millisecond. That would have taken a classical computer 30 trillion years to complete. And a 66-qubit programmable superconducting computer becomes the fastest quantum computer developed. 2022, IBM released a 433-qubit processor. 2023, 2 ions are entangled over 230 meters. Quantum computers will revolutionize not only the computing industry, but the industries of its application. In terms of topical impact, quantum computers will reform artificial intelligence to a level we have never seen before. Whilst AI will become almost synonymous with human intelligence, its applications will become limited and costly to run. Not only that, but it will significantly increase the wealth divide, as the rich use it to get richer. In terms of quantum computing, AI's positive potential, we could use it to help cure cancer or perform high-performance chemical molecular creations. So what are the straight positives of quantum computing? Quantum computing will allow for a significantly stronger encryption scheme to be developed. This means more personal information behind stronger and stronger locks. Currently, theorized quantum encryption schemes are so powerful it would take a quantum computer millions of years to break its own encryption. This would lead to a wealth of secure systems protecting against hackers until at least the next new computer rolls around. Quantum computing has big applications in pharma, and more specifically material and chemical sciences. Before trialing on live animals, scientists must first test on a computer simulation. Often these simulations are slow and buggy. Google's supercomputer array has 120 computers dedicated to pharma analysis, loaded with 17,000 plus protons for interactions, but it still takes well over a week for a single result. With quantum computers, this time could be dropped down to a couple of minutes for all proteins. It would increase efficiency of pharma research significantly, replacing old and slow computer-aided drug design software in use today. This leaves huge room for further innovation, such as dedicated drug discovery and personalized medicine schemes. For any illness or sickness, any slight genetic deviation causing a chronic disease could be treated with a quantum computer's help, reducing the extreme costs for treating rare diseases significantly. Chemical synthesis and materials modeling would be a reformed industry, as materials scientists can simulate their products before creation, and chemists can calculate complex reaction pathways and interactions in a fraction of the time and brainpower. Nanotechnologies would become increasingly easier to attain as quantum computers calculate the creation of a specific functional material with extremely high atom economy and a microscopic size. Quantum computers excel at the chemical nature of calculations due to their ability to simulate quantum mechanics of the atoms they are analyzing. Quantum computers today have redefined the theoretical location of electron clouds to a higher degree than ever before in hydrogen atoms. With more complicated computers and higher qubits, molecule interactions are not far off being calculated. Quantum computers also provide increased healthcare capabilities through real-time calculation reporting. Imagine a hospital full of patients who all need vital monitoring for strokes, but the equipment is too slow to preempt any attacks. Do you have a team of doctors watching every patient for signs? Better still, you could have a quantum computer read their brainwaves and heart patterns and immediately report a stroke well before it begins, like some helper dogs but on a much larger scale. This would help to revolutionize not only medical but also data science industries. Imagine a large array of sensors all collecting data about a particular system, with the quantum computer almost instantaneously calculating, creating graphs, and reporting problems back to the user. A combined benefit of utilizing quantum computing in the data science and chemical science industries is combating climate change. By using the real-time sensors, data calculation, and chemical or material synthesis, quantum computers could create a new generation of electric fuels and carbon neutral or negative resources to help combat our climate issues. Weather simulations and modeling provided by quantum computers would allow for almost perfect day-to-day weather, temperature, and humidity predictions. These largely unpredictable forces of nature would be completely reduced to a matter of when, not if, by the tremendous calculation powers of a quantum computer. Investments and accounting simulations could provide insight into the economic market for governmental services like the RBA to help accelerate the economy to new heights, benefiting an entire society of peoples, although this has some downsides we will come back to. And finally, near-perfect advertising, marketing, and social feeds could be simulated and generated through the use of quantum computing, allowing technologies to identify what is most personal to you and provide you the relevant information in an online space. Negative impacts are something of a major issue when it comes to quantum computers and being in the right hands. Already we have seen fierce competition between private corporation, institutions, and academies for a monopoly on research and development. With the powers of quantum computers, those with access will be able to create the divide even larger if used incorrectly. The financial abilities could be used by the rich to get richer, exploiting the working class further. The use of these super machines could make all the limitations fade away, and with their monopoly on the technology, prevent anyone else from reaching the same level. With a quantum computer and Shor's algorithm, all encryption used today would become pitifully weak. Current encryption in today's technology is performed through RSA, a special algorithm using two extremely large prime numbers to create a public and private key for reading and writing data. With Shor's algorithm, the public key could be reduced to its prime factors, allowing for reading anybody's data created with the algorithm. And a sample has been proven to work already. We are on the brink of a worldwide security destruction, and very soon those with power will dictate if this technology reaches a public level or if it is used for private nefarious needs. All current computer safety and certificate authority security will be able to be faked within seconds, allowing viruses and malicious hackers to run rampant. As a result of Shor's algorithm, all cryptocurrencies like Bitcoin, which are built off RSA, completely fall apart, as anybody can fake transactions by reversing someone else's key. As of the 8th of the 8th, 23, Bitcoin is worth $30,000. When Shor's algorithm reaches the public, this will drop to zero overnight. All web banking would become unsecure and would have to go off for weeks or months as they upgrade to a more secure system that is impervious to fraud through Shor's algorithm. All stolen data, like from Optus's and Medibank's data breaches in 2022, would become unlockable with ease. The dark web have sites solely for trading encrypted data, so that when quantum computers become available to the public, they can crack the data for their own needs. In the case of Medibank and Optus, this would mean millions of people's identities vulnerable to impersonation, my own family included. On a lighter note, manufacturing limitations include the incredible expense in creating a quantum computer, due to the high demand and low quantity of rare technologies used. A good example is the previously discussed Silicon-28, which costed $1.5 million when first created. Another high-cost resource in demand is helium, used in cooling the quantum computer to a few hundredths of a degree above 0 Kelvin, as we are very quickly running out. And beyond simulations and modelling, quantum computers are just a glorified, overcomplicated, and slower rendition of a regular home PC. They are not an alternative, and sadly never will be. They are solely a tool for helping calculate high-intensity superpositional simulations. I'd like to focus more into chemical synthesis and modelling as the specific innovation for quantum computing and its sub-disciplines. Think of a world with levitating cars, teleportation, and cures to every disease or cancer. Right now, that all seems fantastical and beyond the scope of human innovation. But what if it wasn't a human that figured it out? What if it was a computer? In 2010, Harvard and the University of Queensland built a 3-qubit quantum computer capable of simulating molecular systems. They published an article showing energy spectrum of hydrogen atoms at the highest precision of its time. The simple hydrogen atom could be simulated by a computer back in 2010, and its interactions with other molecules easily calculated with today's significantly more advanced technology. In October 2 years ago, the Australian National University set a record for quantum chemical calculations, using a quantum computer to predict the chemical reactions and physical properties of molecular systems with tens of thousands of atoms. These calculations not only work on singular molecules, but due to the exponential capabilities of quantum computers, they can simulate chain reactions of many molecules in an entire system. What this means is the ability to not only simulate molecules, but to use the computer to design and simulate new materials, superconductors, electronics, and most importantly, drugs. So how does it all work? Quantum computers inherently have the ability to simulate their own workings. And what this means is, because quantum computers are made of qubits, and qubits are often cold-trapped ions or photons, they can simulate their own interactions simply by interacting with each other. In essence, it then becomes a modelling problem, with many variables and alternatives. A quantum computer is designed to do parallel computations, so this modelling problem becomes a very efficient problem to solve, when it could have taken years on a conventional computer. It also significantly increases the energy efficiency of calculating and simulating the modelling problem. By writing the currently known rules of chemistry into a quantum algorithm, any quantum computer would be able to simulate an interaction between predefined molecules, or create a molecule of its own following the rules of chemistry. A major advance is the use of simulating electrons and bonding, which when applied to the chemical modelling problem allows for extremely efficient end products with little to no error. Quantum computers can also inherently calculate electron bonds, as talked about before, through a simple quantum algorithm. Quantum AI could also overlink into the modelling application, as the AI could be used to produce a chemical structure for a specific engineering or biological purpose. In today's technology, the use of a quantum computer for chemical modelling and integrating quantum computations into a conventional computer-aided design workflow would increase synthesis speed for both chemical engineers and pharmaceuticals. Computer-aided drug design isn't new, but the quantum applications could increase both success, efficiency, and speed significantly. Currently, the world's fastest protein supercomputers take weeks to solve complex drug interactions. The use of quantum technologies would solve the decade-old problem of optimization for pharma, allowing for quicker turnaround times on medicinal products. Imagine if a computer developed the vaccine for COVID and how much cheaper, faster, and more efficient it could have been. Now, this may seem like a cause for concern. What if the computer messes up? It will still require a practitioner who works in drug design to use the computer. It just reduces the calculation times exponentially, giving more accurate results, allowing for more humane testing and drug trials. Targeting medications and biomedical engineering and electronics as a system would be revolutionized, as the quantum computer could simulate the entire body and the chemical interactions within. Whilst we aren't at that level yet, we can simulate nanotechnologies and protein interactions through computer-aided drug design in conjunction with quantum computing programs. With this accelerated technology, it is predicted that quantum computers could produce the most significant and successful cancer-targeting cell medications in the century. Not only that, but targeted heart and tumor medications could be administered for a fraction of both the cost and danger, allowing for the most safe medical experiences so far. Monitoring robotics could also be administered by drug and targeted medications, allowing for a macro and micromanagement of high-risk patients' health. This would make strokes, heart or asthma attacks, or diabetes sugar levels easily predicted well before it gets to a dangerous level, creating a much safer, humane, and attention-driven experience where a patient's health is being monitored at every instance of time. Pharma itself isn't the only medicinal use for the chemical synthesis application. Public medicine benefits in a more profound way. Imagine a hospital for patients with extremely rare, or genetic issues which differ on a day-to-day basis. Conventionally, this would be an absolute nightmare, as each patient would need a team dedicated to their individual issue. With a quantum computer, not only could you compute all their individual medication suited to solving their issue, it could also do all of them at the same time. Of course, human operation would be required, but the idea of a personalized medical treatment plan could become very real as quantum computing advances in the chemical synthesis industry. In terms of material sciences, the use of quantum computer chemical synthesis could skyrocket us into the 90s rendition of our future, with levitating cars and holograms. The main issue with any kind of advanced technology today is the lack of ambient pressure and temperature superconductors. These materials produce extremely fast circuits and would allow levitation through generated magnetic fields. They are currently used in specialized chemical imagery and electronic machines, but to have them enter production in an environment that doesn't require 0 Kelvin or pascals of pressure well above human survivable limit would mean a revolution in the technology industry. Superconductors would become the new main source of conductor, helping to reform society. Currently, a compound named LK99 has taken the scientific community by storm, claiming to operate at room temperature and ambient pressure as a superconductor. So far, dozens of replication attempts have failed by various reputable universities. Despite the failure of this compound, the use of quantum computers could find a compound and the recipe to make it that fits all of the at-home superconducting requirements. The quantum computer is able to simulate the electrons on compounds and their charge-space interactions, allowing for a large application into electronic works, leaving room for innovations of new and advanced hypermicroelectronics. Quantum computers are also able to simulate static interactions from a physics standpoint, allowing the creation of composites and materials that perform extremely specific goals, like a new plastic that biodegrades and performs as well in 3D printing or additive manufacturing environments. Further potential uses of quantum chemical synthesis could also reform linked industries. For example, electrochemistry and quantum computing could use chemical synthesis and modeling for creating renewable complex fuels, helping to reform climate change by producing a carbon neutral or even carbon negative fuel that operates at a significantly higher efficiency than any fuel before. Advanced reduction and oxidation batteries like galvanic fuel and electrolytic cells can be created to a much cheaper and higher accuracy. Current issues arise with the cost of these cells and requirements of extremely specific and precise membranes to prevent incorrect reactions. The use of a quantum computer could lead to an even further expanded electrochemical series. A new range of synthetic materials could be designed for specific purposes, like space fuel or stronger steel composites that help in construction and the space industries. Quantum chemical synthesis and modeling could also be used for the analysis of unknown chemical or physical questions, like the operation of the black hole, Hawking's radiation, and the operation of Higgs boson or quarks. Quantum computers could truly expand humankind's reach beyond that which we have ever experienced.
What you thinking? Leave that on record spinning. You feel the rhythm going. Legs ain't got time to lay low. Your knees are bending, so it's time to get up and let go. Hey, mama, how's it going? Can see your body